Hey everyone, it's Mr. Anderson. Today we're going to talk about section 5.2.3 in our CPM ebook. And the goal today is to talk about some ways that we can represent a little differently our rules for writing sequences. And what I have today is, I think, going to be very, very manageable, as well as give you the opportunity to do a little practice and broaden your horizons with some of these items. I did take some notes ahead of time, and I'm going to share these notes with you in a moment. But before I do, I'll remind you that we can open up our table of contents once we're logged in. We can pull down the chapter 5 or expand the chapter 5, and here I am in section 5.2.3. I'm going to start with 5-71 today, and like I said, I put some notes down ahead of time, but we've got a sequence that is a very, very nice sequence to work with. And whenever I'm dealing with a sequence, I always like to recognize what my first term is. In this case, my first term is the thing that comes first, t of 1, that's -8. And then what is that common difference? What's my my sequence growing by or shrinking by, what have you. In this case, I know it's going to be a common difference just for some work I did ahead of time. And it's easy to see here as I move from 4 to 10, it's clear that I'm adding 6. And I can verify that. Is -2 plus 6 4? Yes. Is -8 plus 6 -2? Yes. Right? And it also works back the other direction. I can subtract 6. And in part A of this problem, they say, what are 2 ways that you can find the 10th term? And then what is the 10th term? Well, the first method that's always going to work is the plug and chug method. And you guys, believe it or not, have great experience with this. The plug and chug method works great. You just simply are going to add 6 until you get to the 10th term, because that's my difference. So 10 and 6 makes 16, and then I keep going, 22, 20. I'm just adding 6 every single time, and I end up with 46 as my 10th term, right? So I know that that's going to be my 10th term. It's very doable here. It's probably not the best approach, the plug and chug method, if you need to find the 100th term, right? I'd be doing this for a while. It doesn't make sense to do it there. But the other option is to write the rule and do some evaluating. And that's where part B takes us here. Part B takes us to writing the rule, and they introduce some language. They call this the explicit equation. Anytime you have a geometric or arithmetic equation that gives you any term you want based only on the term number, that's an explicit equation. And it's really, really easy to do. Recall that from our last video in section 5.2.2, the slope, right? That's all this is, right? This is the model, the framework is just a fancy version of slope-intercept form, where the slope is the common difference and the intercept is the 0th term. And I'll remind you what that is in just a moment. The common difference, we just said a minute ago, we're going up and down by 6. So I'm going to plug in 6 for that common difference, right? There's if I had a slope triangle, it'd be rising 6 and running 1, right? But what is that 0th term? What would that y-intercept be? And that's actually really easy to see if I go back to my plug and chug method, okay? The first term was -8, so I'll put a blank before that, and I'll work backwards to that. And if I was going forward by 6 by adding 6, I can go backwards by subtracting 6. So I ask myself, what's -8 minus 6, and that works out to be -14. So I know that y-intercept is -14, so -14 should go right here. And of course, you could write that as 6n minus 14 as well. And let's just verify that our 10th term does work out to be 46. I can just say, hey, t of 10, my 10th term, should be 6 times 10 minus 14, or plus -14. 6 times 10 is 60 minus 14, and then 60 minus 14. Hey, there it is. There's the other way to get that 10th term. It is 46. All right. Introducing a new method of writing this rule. Introducing an idea called a recursive equation is what part C is doing. The next term after t of n is called t of n plus 1. All right, where we're taking that n value and we're adding just one more. We're adding one more spot to it. Write an equation to find t of n plus 1 if you know what t of n is. An equation that depends upon knowing other terms is called a recursive equation. And this actually is not all that bad to do. We know that we're taking a term and we're adding 6 to get the next term. That's the plug and chug method. We're taking one, we're adding 6 more. We're taking one, we're adding 6 more. So if I know that in order to find a term, I can take a term I know and I can add 6. Well, if I add 6 to get the next term, that'll give me the t of n plus 1 term, right? The notation here is without a doubt the hardest part to swallow. So this is saying, for example here, if I know the first term, I can add 6 to it and I can get the first and one more, the second term. Okay? I don't often write those things that way, but I can definitely write it this way to show you. Okay? The first term is -8. If I take -8 and I add 6 more, right, exactly what this is telling me to do, add 6 more, does that give me the t of 2, the second term? It sure does. Okay, the other thing that you need really to identify a recursive equation is you also need to list what your first term is. Okay, because you got to let everyone know where you're starting. So your recursive equation may get a little clunky because you do have 2 parts there, and it does matter, right? As we discussed already in some prior videos, the starting point does matter. So be sure to include that. Okay, we're going to keep on keeping on because there are a couple things that I really want to get to here in this video. 72 is a great problem. Alejandro uses recursive equation t of n plus 1 equals t of n plus 1 plus 6 from part C of problem. You know what? Anderson's got a typo in here. This should just be t of n plus 6. Woo, from part C of problem 5-71 to write the following sequence. Does Alejandro's sequence match 571? And the answer is no. And you might say, well, why? What the heck, Anderson? Why? Why does Alejandro's sequence differ than yours? It looks like this matches yours, except for the typo that you made. This matches this part right here. The problem he's got, and this is why it matters so importantly, his first term is 0. Okay, so the important piece here is these two things are not the same, right? So if we want to have a matching recursive equation there, we got to have not only the same rule, t of n plus 6, but also the same starting value. Okay, and that's, I kind of answered part B there. It says, why did he get a different sequence than the one from 5-71? How can you mathematically write down the information he needs so we can get the correct sequence? Stepped on my own touchdown call there. Different starting values, right, is the key feature. Different start values, or different T1s, and that's why we need to include both of those pieces, right? It really does matter. Okay, let's move on to one more idea, and we've got it here in 5-74. We've got to do something using a little bit different of information here. We don't have a start value here in 5-74, but we do have enough information to go ahead and do some thinking here, right? Okay, Avery and Colin were still at it. This comes from 573. I didn't include 573. I'm just going to go ahead and do some work with 574 here. Avery and Colin are still at it. Colin writes the following. He says the second term of a sequence is 19, and he says, using a recursive rule, that the next term is equal to the term that comes before it minus 2. And Avery wants to write an explicit equation from this information. Okay, so here we go. I'm going to go ahead and just do a little bit of work here that kind of diagrams what this is thinking. All right. I don't know the first term of this thing yet, but I do know the second term is 2. And I also know that the term that comes before it, I'm sorry, I made a mistake. The second term is not 2. The second term is 19. My bad. Okay, and I get that information from right here. Okay, the other thing that I can deduce from this is that the next term, the third term, is equal to the second term minus 2. So I can take the second term and subtract 2, and that'll tell me, okay, if I take 19 and subtract 2, I get 17. If I take 17 and subtract 2, I get 15, and so on and so forth. And you guys can now see the pattern. I'm not going up in this particular equation. My common difference is now negative 2. Okay, all right. I can work backwards. I can work this way then. What number do I need to subtract 2 from to get 19? Well, that number is 21. So now I've got a first term. I've got a common difference. I've got a sequence that's arithmetic because I'm going up or down by the same value every single time. I'm going down by 2. And what tells me that is this information right here. Okay. Avery wants to write that explicit equation. Here's a reminder of the explicit format. D times n, plus t of 0. Okay, well this is actually really, really manageable. I'll put a blank in for the slope and a blank in for the intercept. Well, the slope, pretty easy. We can have a negative slope. Slope is just negative 2. But now we need to figure out what that intercept is. All right, ladies and gentlemen, I got to work backwards to figure out that intercept. I got to work backwards one more spot. I'm going to get rid of this brace right here. Okay, if I work backwards one more spot, what number do I need to take away 2 from to get 21? And the answer is, and that's going to be where this thing starts at. The intercept is, where this thing has the intercept. Okay, there is my explicit equation. All right, that matches this recursive equation. They are, in fact, the same thing. It's just a different way to go ahead and write that. Now, here's what I'm going to do. Okay, I'm going to ask you guys to try something right here. Okay, part B says Avery wrote a brand new explicit equation. Avery says t of n equals 6n plus 8. Colin wants to write the recursive equation. So go ahead, figure out where it starts at, and figure out if you can write that in t of n plus 1 form. Pause the video, go ahead and give that a shot, and then unpause it. We'll be back together in a second. All right, I took a couple of notes. Hopefully you would pause the video there. Did you try it? Did you give it a shot? How'd you do? Does what you have match what I have? Let's check it out, right? I went ahead and I documented. I said, hey, the first term here is going to be 6 times 1 plus 8. Now, 6 times 1 is 6, plus 8 is 14. The first term is going to be 14. And then I went ahead and I found the second term. 6 times 2 plus 8, 6 times 2 is 12, 12 plus 8 is 20. So I went ahead and I started my sequence down here. I said, all right, I've got 14, then I've got 20. It looks to me like I'm adding 6 every single time, and my slope supports that. So if I continue to add 6, now I've got that now I've got that sequence generated, okay? But how in the heck do I write that recursively? Well, always start with what your first term is. That's why I needed to do this piece no matter what. I needed this right here. All right, tell everyone what t of 1 is. Okay, 6. 14. And then tell everyone what you're doing to get t sub n plus 1. Well, I take t of n, and then what am I doing? I'm just adding 6. And this right here is a recursive equation, right? Those two pieces. And every time we use the plug and chug method, we use this recursive idea. If, for example, I said find t of 105, find the 105th term, right? Using that recursive equation would be a nightmare for me. I'd have to do a lot of work to get there. But using the explicit one would be much, much easier. Okay? So 2 different tools and 2 different applications for those tools, and hopefully you're in a situation where at least one of those can make your life easier. All right, ladies and gentlemen, I'm going to stop right there. We do have a little review preview for you guys. It is just a couple of problems. Just works out to be 4 of them today. 76, 77, 78, and 80. Go ahead and give those things a shot, and if questions come up, please make sure your questions get answered. Ladies and gentlemen, thanks for watching. Have a great day.